With the emergence of ion exchange application for the removal of natural organic matter in drinking water production, a new kind of waste is generated by utilities. What exactly is the ion exchange brine and how can we best handle it is the topic of this video. I am Elisabeth Vaudevire, technical researcher at PWNT Technologies. In this presentation, we introduce a typical composition for the ion exchange brine, the treatment method currently available, and the opportunity explored by the OC2C project to create valuable byproducts from the brine components. But first, let's describe these components. In a previous video about ion exchange, Eric Kooijman explains the mechanism of exchange between chloride anion at the surface of the resin beds and the anions from the raw water, among which the negatively charged natural organic matter, which leads to a saturated resin. Once separated from the raw water, the ion exchange mechanism at the surface of the resin is reversed by contact with an excess of chloride from a concentrated sodium chloride solution, leaving at the end of the process a resin ready for reuse and a salt solution spot with anions removed from the water that we call the brine. The kind of concentration of anions present in the brine depends on the origin of the water, as well as on the parameter applied on the operation of the ion exchanger. Generally, three kinds of compounds are encountered: the excess of sodium chloride from the regenerant solution, the colorful and negatively charged NOMs, which are targeted by the process, and some inorganic anions commonly present in the water, such as sulfate, nitrate, or bicarbonate. For the locations where brine discharge is not possible or desirable due to high salinity, coloration, a variety of treatment technologies are available to achieve different goals. These goals are discussed here. One commonly applied strategy is the recovery of the excess of chloride to recycle it in the next regeneration process. Taking an example of the water treatment plant at PWN, it's estimated that 20 to 30% of the chloride ions remain in the brine. Recovering this amount will allow to cut back by 20 to 30% the purchase, the transportation, and the production of the salts necessary to pretreat the water. And that showed a positive impact on the overall environmental footprint of the plant. Two technologies were tested in this project: the nanofiltration, which uses pressure to transfer water from the monoselective ions to the permeate, while multiselective ions and organics are retained in a concentrate solution; and electrodialysis, which uses a current to move just the inorganic ions through the membrane, carrying the opposite charge. Electrodialysis can be made selective, so only monovalent ions can transfer. As a result of using one or the other technology, the concentration factor will affect different elements of the brine. In this example, with this brine composition and a recovery of 80% of chloride, we calculated the expected outcomes based on experimentally determined transfer for both technologies. With nanofiltration, the concentration factor affects the natural organic matter and the sulfate retained by the membrane, and partially the sodium being the only cation in solution. This allows a first reduction of waste. With monoselective electrodialysis, the concentration factor affects the sodium chloride and is controllable to desire since no water passes the membrane. The brine is then depleted of part of the salt, which can be helpful prior to an eventual discharge. A second usual strategy with brine treatment is to reduce the volume to a minimum prior to transportation, for example, even all the way to zero liquid discharge. The evaporation technique called dynamic vapor recompression was designed to deal with salt concentration way above crystallization levels. It was tested here successfully, reaching on pilot scale concentration factor up to 100 times. To increase the operational efficiency of dynamic vapor recompression, it can be combined with nanofiltration. A last possible strategy with brine treatment is to achieve the full separation of the major salts and the organics toward the creation of byproducts. In this given example, after the recovery of monovalent salt like sodium chloride for regeneration, natural organic matter can be separated for application in agriculture from the sodium chloride, which itself can be used in glass or paper industry. Once all compounds are separated and reused, we end up with theoretically zero discharge. This brings us to the last part of this presentation and the market opportunities for byproducts of brine treatment, specifically for the natural organic matter. As part of the natural organic matter and subsequently of the dissolved organic matter and the dissolved organic carbon are two specific species, the humic and the fulvic acid. This, thanks to their low molecular weight and high numbers of carboxylic and other active groups, are a prime target on the ion exchange and end up as a dominant part of the natural matter in the brine. In addition to absorbing well on the resin, the previously mentioned property gives the humic and the fulvic acids an important market value, being a natural chelating agent in various industries such as agriculture. Before penetrating these markets, the efficiency of humic and fulvic acids originating from raw water body needs to be demonstrated. Investigating the molecular structure gives us many hints on the ability of the humics to bind essential minerals and pass membranes of living cells, which is essential for a chelating agent. And now, another essential step is to demonstrate the benefits of adding these humics, either to crop growth or to animal health in real conditions. And finally, developing a production method that meets the requirements of byproducts quality and the cost effectiveness. And finally, doing this. This part of the research is still going on. But I hope this video could clarify the notion of ion exchange brine and the elements of this composition, as well as the notion of brine treatment and the different goals, namely sodium chloride recovery, zero liquid discharge, and byproducts creation that can be aimed at. Finally, I hope I made a convincing case for the relevance of the research effort toward humic and fulvic recovery from the brine to enter agricultural market through circular economy. Thank you for your attention.